professor at the Tecnológico Instituto of Buenos Aires and also an adjunct professor at the University of Buenos Aires. He's well known for his work on switch systems, and today he's going to be talking about some new results on guaranteeing uniform global asymptotic stability. Thank you for visiting us.
Thank you, Ricardo, for the introduction. Okay, in this presentation, I will talk about uniform asymptotic stability of switch systems. Switch system is a kind of hybrid system which have been attract a lot of attention from the control community since at least 3 decades. Switch system serves as models for many natural and artificial systems, especially those systems which have abrupt change in its dynamics. The stability properties of switch systems has been studied since the beginnings of the switching system theory, but it is still a topic of current interest because there are many open problems. We will start with some background on switch system. The class of switch system we consider here are time invariant switch systems. We have a finite family of continuous vector fields, and the switch system is modeled by this differential equation. Here, x is the state variable, x is in Rn, sigma is the switching signal, that is a PSY constant and continuous from the right function. The times where sigma is discontinuous are called the switching times. We suppose that on each compact interval there are a finite number of switching times, so no signal behavior is assumed. Each vector field generates a dynamical system given by this equation, and this system is called a subsystem of the switch system. Subsystem or mode of the switch system. The notion of solution is given here. Given a switching signal, x is a solution of the switch system if x is continuous, and between consecutive switching times, x satisfies this differential equation. Between consecutive switching times, sigma is constant, so x is a solution of one of the subsystems of the system. So a solution of a switch system is a concatenation of solutions of the subsystems. And the switching signal at each time indicates which subsystem is active. We say that a pair x sigma is a trajectory of the switching signal system if sigma is a switching signal and x is a solution corresponding to this switching signal. In many cases, one is not interested in all the possible trajectories of the switch system, but in a subclass of trajectories. We are interested in a family of trajectories. For example, one can be interested in the trajectories whose switching signal are periodic or have some dwell time or verify some state-dependent constraint. About dwell time constraints, I will define some type of this type of constraint. We say that a switching signal is dwell time if the distance between consecutive switching times is bounded from above from a constant tau d, this constant tau d is called the dwell time of the switching signal. This means that if a mode is active, then it is active for at least tau d units of time. Another constraint on the switching signals is the average dwell time. A switching signal is average dwell time if the number of switching times in the interval AV is bounded by this expression. N0 is called the shutter bound, and tau d is the average dwell time. Another constraint is persistent dwell time. A switching signal is persistent dwell time. See if there exists a constant tau d and t, positive both positive, so that in each interval of length t, some mode is active for at least tau d units of time. One can prove that a dwell time switching signal is also an average dwell time switching signal, and that an average dwell time switching signal is at the same time a persistent dwell time switching signal. Sometimes the trajectories of the switch system satisfy some kind of state-dependent constraint. In some situations, the mode which may be active depends on where the state is. This is formalized through this definition. Suppose we have a family of closed subsets of Rn, one for each mode, and such that the union of these subsets are Rn. This is called a covering of Rn. For each x, consider the set of index where x belongs to Chi. We say that the trajectory is invariant with respect to the covering if it satisfies this condition, or equivalently this condition. In this picture, I explain a bit this kind of a state-dependent constraint. When the state is in this zone, then only mode 1 can be active. When the state is in this zone, only mode 2 can be active. When the state is in the intersection, and then mode 1 or 2 can be active. Then the set Chi indicates where the modes I can be active. If for a given state, more than one mode can be active. For example, in this zone, 1 or 2 can be active. Okay. Some about the stability of switch system. We are interested in the stability of families of trajectories, not in the set of all the possible trajectories of the switch system, but in a family of trajectories which we are interested in. We consider the following definitions that are natural extensions of the traditional Lyapunov stability properties. The first one is global uniform stability. This condition is uniform Lyapunov stability. And the second condition is uniform boundedness of the trajectories. We say that the family of trajectories is globally uniformly stable if it is locally uniform stable and uniform bounded. We say that the system is globally asymptotically stable if it is globally uniformly stable and every solution in the family converges to 0. And we say that the family is globally uniformly asymptotically stable if it is globally uniform stable and the convergence to 0 is uniform in compact set for the initial conditions. In other words, given epsilon and r, there exists a time t so that if the initial condition is in the ball of radius r, then the trajectory is in the ball of radius epsilon after t units of time. This part is called uniform attractiveness of the equilibrium point. The uniform stability and the uniform asymptotic stability can be formulated in terms of k infinity and kl functions. The global uniform stability is equivalent to the existence of a k infinity function satisfying this inequality. The uniform asymptotic stability is equivalent to the existence of a function of class KL satisfying this inequality. For all t zeros, this is this inequality has to be held for all t zero. Once yes. Once the solution enters the ball of radius r, time unit of time later, the solution have to enter the ball of radius epsilon. The solution, T0 is not necessarily the initial time of the solution. The initial time of the solution could be 0, for example. The initial condition could be in another ball. But once the solution enters the ball of radius r, times units of time later, the solution have to enter the ball of radius epsilon. This for this reason, this has to be held for every T0. For non-switch time invariant systems, asymptotic stability and uniform asymptotic stability are the same. For time variant, no. For time variant system, asymptotic stability and uniform asymptotic stability are non-equivalent. But for time invariant, these properties are the same. For families of switch systems, for families of trajectories of switch systems, the equivalence doesn't hold. This is an example. We consider here a switch system with two subsystems. The first one is stable, but not asymptotically stable. the trajectories of this system are circles, and for this mode is asymptotically stable, and the trajectories are rays converging to 0. We consider the family of trajectories defined in this way. Is composed by all the pairs x sigma, with sigma in the family S, where the family S is the elements of the family S are switching signals that satisfy this condition. For each switching signal sigma in S, there exists a time is sigma, such that mode 1 is active until the time is sigma, and mode 2 is active after time is sigma. This is a trajectory of the first subsystem. This is the initial condition. The solution of a trajectory of this example looks like this. Suppose we start at time 0. Between time 0 and time t sigma, mode 1 is active, so the trajectory looks like this. And when in this point, there is a switch to mode 2, and then the trajectory looks like this. So every trajectory in this family converges to 0. But the convergence is not uniform because the time is sigma could be arbitrarily large. So for families of switch systems, this equivalence doesn't hold, and this complicates the analysis of stability. Now we give classical results on stability, which is based on Lyapunov functions. Suppose we have a family of functions, bi, one for each subsystem, so that bi is a Lyapunov function for subsystem I. It is differentiable. It is positive, definite, and radially unbounded. And the derivative of bi along the trajectories of subsystem I are negative semi-definite. The first three conditions say that bi is a Lyapunov function for the subsystem I. We add the condition 4, which is a condition on the switching times, and which can see this condition in this picture. If we take, we define this function, when mode 1 is active, the function b coincides with b1, and then it is decreasing. When the system switch from 1 to 2, the function b1 is greater than the function b2 because of this condition. Then the function b jumps downward. And in this zone, the function b coincides with function b2, and then it's decreasing. And at this point, there is also a jump, but the jump is downward. So the function b is non-decreasing. Then, so you have these 4 conditions, then the family of trajectories is globally uniformly stable. If in addition these functions hi are positive definite, then the family is globally uniformly asymptotically stable. In this case, in which the functions hi are positive definite, the function b are strictly Lyapunov functions. When these functions are also non-negative, are only non-negative, the functions bi are weak Lyapunov functions. Non-increasing, yes, non-increasing. The derivative is non-negative. Okay? Okay, it's okay, yeah. You are right. The function is non-increasing. Okay, sorry. Or decreasing, but not non-decreasing. Okay. Okay. Then, weak Lyapunov functions are easier to find than strict Lyapunov functions because in many cases the subsystem have a dissipative model, and the storage function is usually a weak Lyapunov function. In some examples, for some subsystems, there are no strict Lyapunov functions because, for example, the subsystem is stable but not asymptotically stable. This is an example. This subsystem is stable but not asymptotically stable. So for this subsystem, there is no strict Lyapunov function, but there are one which is weak Lyapunov function. So this motivates this problem. Assuming the existence of a family of weak Lyapunov functions, find additional conditions for ensuring the globally asymptotic stability or the globally uniform asymptotic stability of a family of trajectories T. There are many results for this problem. For example, extensions of Lassalle's invariant principle, starting with the paper of España in 2004. There are results more recent, for example, this of 2014. There are also convergence results. These are some of the papers which give that type of results. And there are results based on detectability and output persistently exciting conditions, which are in the papers of Tichun-Lee and collaborators, which starts with a paper in 2008, and a more recent paper is in this year. The results in the first two groups mostly assumes dual time conditions. Most of them assume that the switching signal verifies some dual time condition. And also give conversion results, but not uniform conversion results. The papers of Tichun-Lee give conditions for uniform asymptotic stability and doesn't involve any dual time condition. So I will follow this paper in the following. The conditions in the paper of Teacher Lee are based on detectability conditions on switch systems, and I'm going to make some review. Suppose we have a switch system, but with an output. We say that the pair HF is output persistently exciting, OPE, with respect to a family T of trajectories. This is defined for families of trajectories, not for the whole of the switch systems, just for a family of trajectories. So the pair is OPE with respect to a family of trajectories. For every positive epsilon, there exists a positive number T and a positive number R, such that the following implication holds. This says that see the solution stays in this donut, in this donut. For at least T units of times, then this integral is at least R. T and R depend on epsilon, or depend on the dimensions of the donut. Then, with this definition, we have the following result. This is a theorem of Teacher Lee and Yang, appearing in the transactions on automatic control in 2008. Given a switch system with outputs, and a family of trajectories, if this family is uniform stable, these integrals satisfies this inequality. This say that if the solution is bounded, or if the solution stays in a ball of radius R, in the interval St, then the integral between S and T is bounded by this constant M, and this constant M depends on the number R. In other words, for bounded solutions, these integrals are uniformly bounded. And third, if the pair is output persisted excited with respect to the family of trajectories, then the family is globally uniformly asymptotically stable. This result is interesting because it doesn't involve any dwell time condition. Here we are not supposing that the switching signal satisfies any dwell time condition, and this is a uniform asymptotic stability result. What? No. Maybe yes. No fix. If in the interval, St, the solution is in the ball of radius R, then the integral is bounded by M. Okay? S and T could be, this T could be infinity. In the case the solution is in the is bounded from S to infinity. Not necessarily, because we can have a trajectory like that. This is time S. This is time t. While the trajectory is in this zone, then the integral is finite, is lower than m. But the trajectory could be exceed the ball of radius r. Okay? If the trajectory is in the ball for all time, then the output is integral. Okay, so this is a very nice result because it gives uniform asymptotic stability and it doesn't involve any dwell time condition. The problem is that it is hard to check that a pair HF is OPE. It's very hard to check from the very definition. For non-switch systems, a pair is OPE if the system satisfies this detectability condition. That says that given a bounded solution of the system, if the output is 0, is identically 0, then this infimum is 0. In other words, if a bounded trajectory of a bounded solution of this differential equation stays away from 0, it cannot produce the identically 0 output. This is for non-switch systems. What is the equivalent condition for non-switch system in terms of a detectability condition? This definition was given by Teacher Lee in 2015, very recently, and involves the concept of T zeroing output sequences, which is here. We say that a sequence like that is a T zeroing output sequence if TK is a sequence of numbers, of real numbers. This condition implies that Tk goes to infinity when as k goes to infinity, and xk and sigma k are a trajectory of tau for all k. For all k. The second condition says that for t in this interval, the solution xk is in this donut, and the donut, this donut is the same for all k. This interval, the length of this interval is increasing with k. And the third condition says that this limit is 0. that is the output is 0 or converges to 0 as k goes to infinity. The definition of weak zero state detectability given by teacher Lee is that a pair is weak zero state detectable with respect to a family of trajectory if there does not exist any tau zeroing output sequencing. Very complicated, the definition, because involves sequences, and it is very difficult to check. But with this definition of detectability, one have this equivalence. The pair HF is open, persistent excited. With respect to tau, see, the pair is weak zero state detectable. OPE and this detectability condition are very hard to check from their definitions. So simpler sufficient conditions for them are needed. The limits of tau zeroing output sequences of this type of sequences should give information about the detectability or about the weak zero state detectability of the pair. The problem is that what is a limit of a sequence of this type? What are the limits of this type of sequences? We have to define what a limit of this type of sequences means. Once we have defined what a limit means, one have to characterize these limits. We have two problems. Define what a limit means and characterize these limits. If one obtain these limits and characterize them, one can study the detectability of the pair. To do so, we need to embed the switch system into a control system. In order to define the limits of this class of sequences, we need to embed the switch system into a control system. This control system is a control affine control system with this output, where the controls for these systems are those which satisfy these constraints. In other words, the controls of this system takes values in the convex hull of the canonical vectors or R capital N. And we have to identify the trajectories of the switch system with the trajectories of this control system. For that, we convert a switching signal into a control via this equality. We assign for the value sigma t the canonical corresponding vector in area. With this conversion, a trajectory of the switch system coincides with the trajectory of the control system. This control system has more match trajectories than the switch system. The switch system is embedded into this control system, but the control system has more match trajectories. we need to consider the following type of conversions in the space of controls. We say that a sequence of control converge weakly to a control U. See if for all integrable function f, this limit coincides with this integral. This is a classical definition of weak convergence. You can find it in the book, in the Sontag's book of mathematical control theory, or in any book of functional analysis. This type of convergence is has a nice property because with this type of convergence, the set U of controls is sequentially compact. That is, for each sequence of controls, we can find a subsequence which converges to a control in the same space, in U. Then we have the following definition. A pair bar x bar u, where x is a function from R to Rn, and u bar u is a control, is a t zeroing output limiting trajectory if it is the limit of a t zeroing output sequence. Okay, we have defined what a limit of a t output sequence means. This sequence converges to this trajectory if the x part converges, the translations of the x part in take k converge to bar x uniformly on compact sets, and if the translations of the switching signals converge to the control bar u. We have the following lemma. Given a t zeroing output sequence, always there exists a subsequence of this sequence such that this subsequence converges to a pair bar x bar u. So the set of t zeroing output sequence is sequentially compact. Given a sequence like this, we have a subsequence which converges to a t zeroing output limiting trajectory. On the right-hand side of the the modes only are continuous. The modes and the output. For a fixed mode, the vector field is continuous, and the output map have to be continuous. No. The trajectories of the switch system? No. The limiting trajectories are complete, not the trajectories of the switch system. The trajectories of the switch system could be not complete, but these limits are complete. Eh? The sequence it is not necessarily complete. The sequence, it is not necessarily complete, but the limiting trajectories are complete. Think about suppose you have a sequence of trajectories like this. This is x1. It is not complete. X2 is this. X2 is not complete. And so on. The sequence xk converges to 0. And this trajectory is complete. Do you understand the situation? Okay. Yes. So but each trajectory could have a finite escape time. Okay. But the limit could be is defined for all time. The switching signals are defined for all time, and the limits of the switching signal are defined for all time. But the solutions, the X part, could be had a finite escape times. But the domain of each part X is increasing. We have the following lemma. Oh, okay. So the E0 in output sequences are sequentially compact. This is a fair result. This is given by this lemma. The family of trajectories may satisfy some type of constraints. For example, they could be invariant with respect to a covering. Okay, if the family of trajectories is invariant with respect to a covering, the limits are invariant with respect or satisfy some kind of a state-dependent constraint. So if the family of trajectories satisfy a state-dependent constraint, the limits also satisfy a certain kind of state-dependent constraint. This constraint, the constraint is given in this lemma. Given a covering, for each state X, we define this set, which is the convex hull of the canonical vectors for which X is in the GI set. And then the control bar U have to belong to this set for almost all T. This is a kind of state-dependent constraint for the trajectories. The invariance with respect to a covering is traduced in this type of constraint. And if the switching signal satisfies some time-dependent constraint, we also can traduce this time-dependent constraint in a constraint for the controls by taking this set. This set contains all the limits of translations of switching signals. We consider the translations of switching signals, syncing the switching signal as controls via the identification, and we can construct this set, and this set contains the time-dependent constraints on the switching signals. So the limits of these sequences also satisfy some kind of constraints that we can find. I go to define the notion of reduced control system. Suppose that the vector field Fi can be decomposed in this way. This part is 0 when the function hi is 0. When the output is 0, then this part is 0. This is for simplifying the dynamics of the reduced control system. We always can take this part as 0, then hat Fi and Fi are the same. But we can put here any other function which satisfies this implication in order to simplify the dynamics of the reduced control system. And this is the reduced control system. This is a control system where the output is constrained to be 0. The controls are constrained to verify the state-dependent constraint on the limiting controls and to belong to the set of limits of the translations of the switching signals. This is a reduced control system because there are some trajectories of the control system, but not all the trajectories of the control system. The important result is that, well, this is a definition. A complete trajectory of this system is a pair xu where x is locally absolutely continuous, u is a control which belongs to this set and satisfies this constraint for almost all t. X, there is an error here. It's have to be a hat, not Fi. You know, a hat. X is a solution of this equation with hat Fi instead of Fi, and E has to be 0 for almost all t. A pair satisfying this four condition is called a complete trajectory of this reduced control system. This reduced control system could have no solution except the trivial one, x equal 0 and u. But it is not a problem in this context because we don't have to look for the solution of this system, but given a solution of this system, we have to analyze some properties of this solution. We don't have to solve this system. We only have to check that the complete solutions of this system satisfy some condition. This lemma characterizes the limits of T0 in output limiting trajectories. Every limit of T0 in output limiting trajectory has to be a solution, a complete solution of this system. So, by analyzing the solution of this system, we are analyzing the behavior of the T0 in output sequences. For this reduced control system, we have this definition of the weak zero state detectability. We say that the reduced control system is weak zero state detectable if for every bounded complete solution of sigma, this infimum is 0. This is an analogous condition for the condition of detectability in the invariant, then in the non-switch system. This is analogous to this. In this case, there is only one subsystem, so the reduced control system for this subsystem, for this system is dot x equal f and e equals 0. And then the condition of detectability is that if we take a bounded solution of this and the output is identically 0, then the infimum is 0. Okay, this is the main result of this presentation. Suppose we have a family of trajectories that are invariant with respect to a covering x, chi. Suppose that the reduced control system is weak zero state detectable. Then the pair HF is weak zero state detectable. And in consequence, the pair HF is OPE. Note that for checking that a pair is weak zero state dependent from the very definition, we need to check what happened with sequences of trajectories. And in this result, we only have to check what happened with the complete solutions of this system of equations. Here we have not we don't have to deal with sequences, but with solutions, which is easier. Okay. From this result, we can obtain the following criterion for uniform asymptotic stability based on weak Lyapunov functions. Suppose we have a family of trajectories that are invariant with respect to a closed covering. We have a family of weak Lyapunov function which satisfies. No puedo apretar ahí, ¿no? Ah, con esto. The family satisfies these conditions. And we consider the corresponding reduced control system. Here, HE is the derivative of the Lyapunov function along the trajectories of the subsystem. If this reduced control system is weak zero state detectable, then the family of trajectories is uniform asymptotically state. So, we have a family of weak Lyapunov functions satisfying the conditions of the classical theorem, and this reduced control system is weak zero state detectable, then the family of trajectories is uniform asymptotically stable. This result doesn't involve any dwell time condition and take into account the possible constraints the trajectories verify. I will omit the proof. Just some examples. Suppose we have a switch system with two subsystems. The trajectories of the first subsystem are like this. This is the spirals running clockwise. And the trajectories of the second mode are look like this, are spirals running counterclockwise. If we take the family of all the possible trajectories of this switch system, this family is not asymptotically stable because there are trajectories which do not converge to zero. This can be easily seen by taking the differential inclusion defined by the convex hull of this vector field. This differential inclusion have more than an equilibrium point. So there are trajectories of the switch system which converge to these equilibrium points, and there are trajectories which do not converge to zero. So we have to restrict the family to obtain asymptotic stability. We consider the following switching rule. A switching from mode 1 to mode 2 is only allowed if this product is non-negative. And a switching from mode 2 to mode 1 is only allowed if this product is non-positive. This picture illustrates the situation. When the state, when X is here, if mode 1 is active in this zone or in this zone, then one can switch from 1 to 2. One can switch or not. It is not mandatory to switch from 1 to 2 in this zone. But if mode 1 is active in this zone, then if you want, you can switch to mode 2. If in this zone mode 2 is active, then you can switch to 1. You cannot switch to 1. So if in this part is mode 2 active, or to have a switching, you have to abandon this zone. You have to enter in this zone or in this zone. And some similar occurs in the blue zone. If the state is in this zone and the mode 2 is active, then you can switch to mode 1 if you like. And if mode 1 is active in this zone, you cannot switch at all. For example, one possible trajectory of this, with this rule could be maintain mode mode 1 always active, or maintain mode 2 always active. But you can have trajectories like this. On this axis, if you stay in mode 1, you can switch to mode 1. But if you stay in mode 1, you also can switch to mode 2, because this axis is in the intersection of the two zones. So we start here with a solution or with mode 1 active. In this zone, you can switch to mode 2. So you here switch to mode 2, then you move in this way. When you arrive to this point, you can switch to mode 1, and then switch to mode 1, mode 2, and so on. So you can obtain a trajectory like this. If you select the switching times in a suitable way, this trajectory doesn't satisfy any dwell time, because the times would be arbitrarily small and goes to 0 if you like. Okay, we have the family of trajectories which satisfy this switching rule. We will prove that this family is globally uniformly asymptotically stable. We consider the following Lyapunov functions. This for mode 1 and this for mode 2. They are different, one for each mode. The trajectories of mode 1, the derivative of this Lyapunov function for the trajectories of the first subsystem satisfy this equality, or then it is non-positive. And the derivative of the second Lyapunov function along the trajectories of the mode 2 satisfy this equality, and it is not negative. So B1 is a weak Lyapunov function for mode 1, and B2 is a weak Lyapunov function for mode 2. B1 is greater than B2 in this zone, and B2 is greater than B1 in this zone. This picture is useful for see that. When you stay here, B1 is greater than B2. So if mode 1 is active and you switch to mode 2, the Lyapunov function is lesser than the Lyapunov function B2 is lesser than the Lyapunov function B1. So the Lyapunov function evaluated along the trajectories, these trajectories is always non-increasing, because the same happen in the blue zone. So this family of Lyapunov functions satisfy the condition of the classical theorem based on multiple Lyapunov functions. Now we consider the following reduced control system. This is the system we have to analyze in order to get a uniform asymptotical stable result. Note that H1 is 0 when X1 is 0. This is an error there. Here it could be X1 and the here and the same. It's an error here. And this function is 0 when X1 is 0, and this function is 0 when X1 is 0. So we have take as hat F1. These parts are 0 when the output are 0, and we have as hat F1 the vector field composed by this and this. And the same for the second mode. So this is a reduced control system. We have to analyze, here we have no consider a state-dependent constraint. Un minuto. Okay. Here we have no consider a state-dependent constraint or time-dependent constraint. So the set of controls only have to satisfy this. So suppose we have a solution for this reduced control system, a complete solution for this control system. From this equation, X1 have to be 0 for all time. So its derivative have to be 0 for all time. So this is 0. Then this part have to be 0 for all times. Then 12 U1 have to be equal to U2. With this information, we obtain the following. U1 is this fraction, and U2 is the difference of this one and this fraction. Okay, we obtain the values of U1 and U2. And then we go to the second equation and obtain the dynamics of the X2 variable. The X2 variable have to satisfy this equation. But this equation says that X2 goes to 0 when t goes to infinity. So every complete solution of this reduced control system satisfies the condition that the infimum is 0. And then the family of trajectory is uniform asymptotically stable. The interesting fact is that this family of trajectories doesn't satisfy any dual time condition. Okay. That's all. I want to apologize about my English. I hope you have understood what I say. What? This example. the this I gave only one example. No two examples. Huh? Only one example. So, the example I gave was this. How we obtain the switching rule? There is not a method for obtaining the switching rule. I think I start with the Lyapunov function. I start with the Lyapunov function. We know that this is a Lyapunov function for the first subsystem, and that this Lyapunov function for the second subsystem. And then we elaborate it. We elaborate the rule in order to obtain this condition. In order the family of Lyapunov functions satisfy the conditions of the theorem which guarantees stability. This is a method for designing, stabilizing switching rules. Start with the family of Lyapunov function, and there define the switching law, the switching rule, in order to obtain these inequalities. In some region, you have that B1 is greater than B2. So in such region, you can switch from mode 1 to mode 2. In another side, in another region, you have that B2 is greater than B1, so you can switch from mode 2 to mode 1. If the union of the regions are the whole of the state space, then you have a rule that guarantees that the switching system is stable. Another question? Let me know when to stop. Yes, Lyapunov stability depends on how the switchings are selected. Okay? If you have a common Lyapunov function, the function bi are the same, then you have a Lyapunov stability for arbitrary switching. But in the case you have different Lyapunov function, you cannot have a Lyapunov stability for the whole set of trajectories. But for a restricted one. Okay, another question? Hey. Okay. Thank you.